sapphire laser. Thank you.
Thank you very much. So welcome to this presentation on the titanium sapphire laser. This summer, Professor Michel Pichet asked me to make him a titanium sapphire laser from basically nothing. So that was a really great project. I enjoyed it a lot. Here we go. I start with the context behind the project, why I had to make that laser. Then I quickly see the theory. I'll explain my setup and the results. Here we have a thulium doped fiber laser. Why that laser? Because the final objective of the project is to characterize the thulium population dynamics, the population in the electronic levels. That kind of laser emits at nearly 2 microns. That wavelength is well adapted to materials processing, remote sensing, and biophotonics, like laser-based surgeries. But we need to understand better the population dynamics. Here we have the electronic levels in the thulium silica doped with thulium ions. To have a better understanding on the dynamics that involves several ions at the time, we have to pump it at well at 800 nanometers, so we could measure the decay rates of the transitions. We need the pulses of 800 nanometers to be pulsed with short enough pulses to observe these pretty fast decay rates. So pulse light at 800 nanometers, the best choice is titanium sapphire. It emits at 800 nanometers, absorbs at nearly 530, that is easy to get with Nd:YAG laser doubled in frequency. We had a couple of those in our labs, so it's a good advantage. Next, we can have pretty short pulses easily with titanium sapphire. Next, I see the theory behind the laser quickly. The dynamics in the titanium sapphire are pretty simple. We can reduce all of its electronic levels to a 4-levels model. Most of the time, in normal conditions, most electrons are in the fundamental level, in N1, and they are less and less in the higher levels. So we have to pump the electrons from N1 up to N4. So when they are there, they decay in the lower levels by themselves. And to have a lasing effect, there are another condition is that the decay of entry has to be a lot slower than the other decays. So the electrons accumulate in entry. Once we have a good population in entry, N2 has to be fast. So like this, the electrons accumulate in entry, and we have what we call a population inversion. We have more electrons in entry than in N2. So when we apply a signal at the energy of the gap between N2 and N3, in that case it's 800 nanometers, that signal won't get absorbed but amplified. So once we have our amplification, we want to create resonance. To have resonance, it's easy. We put the crystal in an optical cavity, simply 2 mirrors, with one of them partially reflective. So light goes from a mirror to another, gets amplified at its passage, and a part of it gets ejected, and this is our output beam. So now we take all these concepts and make reality with them. To pump the titanium sapphire, to make them pass from N1 to N2, we need the 532 source. That is the Nd:YAG laser here doubled in frequency. It's doubled because normally it emits at 1064 nanometers, but with a nonlinear crystal, we can double the frequency at 532. It has a very low repetition rate. It's 10 Hertz. So every pulse contains a lot of energy. This one can go up to maybe 600 to 700 millijoules by pulse. It has nanosecond pulses. So because titanium sapphire has a really quick response, it's gonna have nanosecond pulses. That's short enough for our needs. There is my titanium sapphire crystal right here. It's about 3 millimeters wide and 8 millimeters long. And once we reunited the sapphire, the NDI laser, a bunch of mirrors and lenses, here is my setup. The crystal is right here. It's cooled by a Peltier effect, and it is in between the two mirrors of the cavity. If I add the optical paths, in green we have the pump from the NDI laser. It's supposed to be right here, we don't see it. The pump goes here. In red, it's the 800 nanometers wavelength. So first the pump passes through a nav wave plate that sets the polarization horizontally. We need that because the crystal is cut at the Brewster angle, so most of the beam gets transmitted in the crystal and get absorbed. Here we got a lens to adjust the radius of the beam to the crystal. Then it gets absorbed, and the 800 nanometers that comes from the crystal get trapped in the cavity, gets amplified, and goes out by the partial reflective mirror right here, goes to the left, is separated by the correct mirror, and here we have the output beam at 800 nanometers that we need. So here are some results. There is the spectrum of the output beam. As predicted, it's at 800 nanometers. That's good. It's pretty large. The emission band is pretty large.